This lens has an optimal focal length of 1500 millimeters or 59 inches and produces instant fire. Because of the longer focal length, like all optical imaging lenses, this concentrated image of the sun is larger than that of a lens with a shorter focal length, measuring 1 inch across or 25 millimeters. It was not long before clouds paused our experiment. Once the skies cleared a bit, I filled an evacuated tube containing 230 milliliters of water or 8 ounces with a starting temperature of 16 degrees Celsius or roughly 60 degrees Fahrenheit. I have demonstrated evacuated solar tubes in previous videos. The double-walled tube is similar to that of a thermos, but the clear outer glass allows sunlight to absorb on the second wall, transferring heat to the inner vessel, while a vacuum dramatically reduces thermal heat loss into the atmosphere. Placing the tube at the optimal focal length, our first test failed as the lens was focused too high and melted the copper wire. To gauge the optimal focal point, I used the leg of our 1/8 inch thick steel easel stand, and Big Daddy melted a hole in the steel almost instantly, creating a beautiful orange pool of molten metal. The next part of this video is 100% real time. Keep in mind, our starting temperature is 16 degrees Celsius or 60 degrees Fahrenheit, and we are heating water at 7 feet above sea level with no cap on the top. I used a stick to ensure our focal point is optimal. In just under 35 seconds, the water started to boil. After 60 seconds, we had a raging boil that was very intense. A lot of press coverage recently has focused on the usage of nanoparticles for solar collection. I was a bit disappointed when I saw a demonstration of nanoparticles heating water with the addition of concentrated solar, so I decided to take steel drill particles and replicate the nanoparticle test with my lens. Even though the shavings are shiny, they have an enhanced surface area and absorb a lot of light. Even though the glass is clear, the particles are in direct contact with the water. Instantly, the water begins to boil inside our borosilicate glass tube. In under 10 seconds, our water is at a raging boil, and within 60 seconds, the water has bubbled away and evaporated, leaving only the steel shavings, which glowed orange hot and began to melt. The heat was so extreme, the clear borosilicate test tube melted from the radiating heat of the steel shavings, leaving us with an interesting shape. Time to break out the high-speed camera, set at 1200 frames per second, stretching 1 second of time into 40 seconds. Take notice of all those beautiful aqua lenses. When the cool water from this water hose contacts the heated glass, it shatters, creating a dramatic effect. With the lens now focused again on the steel easel, when water is added, you can see the tremendous power of concentrated sunlight boiling away the water almost instantly. Removing the exposure of light from the steel at 1200 frames per second, the water appears to dance on the surface of the steel. Once the stored heat in the steel is absorbed by the water and radiated into the surrounding atmosphere, the water now clings to the steel surface and rapidly evaporates. By slowing the flow of water down, the temperature of the steel rapidly increases, creating the Leidenfrost effect. Here is the Leidenfrost effect at 600 frames per second. The Leidenfrost effect occurs when a liquid comes in near contact with a surface significantly hotter than that of the liquid's boiling point. A cushion of insulating steam vapor protects the liquid from boiling. Clouds soon spoiled our fun for the day, and this is what remained of the Pyrex glass test tube. I'm your host, Dan Rojas. Thank you for watching and enjoy our video.